At this point, we should be asking ourselves not just do linear functions have inverses, but what would that inverse even look like? Can we actually find the function once we know what the forward transform is? In other words, can we find the formula for L inverse? Well, what do we mean by that? Notice first that we are talking strictly about the same input and output spaces because we're assuming there is an inverse to find. Let's make this crystal clear, well, as clear as possible. It's a bit confusing because we have two different spaces that are the same dimensionality. So I'm going to call them dimension 1 and 2, or input and output. What do we mean by finding an inverse? Well, what we mean is that for each b, which is an element of Rn, this is why we have the 1s and 2s. Where's this b? Is it in the input? It's in the output space. So for every b that I can find in this output space, the value x, which is equal to the L inverse of b, so this b is in the second space, and this x then is the unique input x inside the first space. Again, can't tell the difference because they're both Rn, but take an x from here such that the thing that we know what L is. So we can say that L of x equals b. We know x, when we map it, turns into b. What we're interested in for the inverse is, given a b, what's the x? Another way to say that is if we started with x and mapped it with L, that would give us this mysterious b value here, or intermediate b value. And what we want is an inverse that's going to get us back to that x value. So exactly what you saw earlier with regular functions and relations in high school. Start with a value, run it through a function. The inverse is what gets you back to that original value, or here vector. Now it should come almost as no shock at all that if we start with a linear transformation, then guess what? Our inverse is also going to be linear. It's going to satisfy all the requirements about the zero vector, and the order of sums or the order of scalar multiplication doesn't matter, all that stuff. We will not go through the full proof for that. What we are going to care about is that L inverse must also have its own matrix then, because every linear transformation has its own matrix. So again, so far we've seen existence type proofs or constructions. What we're going to get into now is if someone gives you a matrix A and you want to undo it, there's going to be some matrix A to the negative 1, or we often just call it A inverse, which is going to be a n by n matrix 2, and it's going to be something we can build. Unfortunately, it turns out to be not a horrible construction either. If we have an invertible matrix, what we can do is build the following double width matrix. So this is our original A, this is our forward operation. And after the original matrix, we put the n by n identity matrix, which you've seen earlier. But just as a reminder, this is the matrix that has 1s down the diagonal and then has zeros everywhere else. 0, 0, 0, 0, 0, 0, 0, 0. You get the idea. 0, 0, 0, 0, 0, 0. All right. So 1s down the diagonal, zeros everywhere else. The way we are going to generate the inverse matrix, A inverse, is we just crank through row reduced echelon form on this left-hand side until we get an identity matrix on the left. And what we're going to have as a consequence, or following along on the right, is the inverse matrix of A. Let's work through some examples because that really brings it home. If we look at this 2 by 2 matrix here, which we can see is invertible because the columns are linearly independent of each other, they're not multiples, then we should be able to compute the matrix for A inverse. So what we're going to do is construct our double-sized matrix here. We're just going to copy A down, 4 and 7. That's our A. And then you can I put a vertical bar just to keep the two separate in my mind, so you don't have to. And then we have this, which is the 2 by 2 identity matrix. All right. And our goal is to get the left-hand side of this part here, into an identity matrix again. So we're going to turn this into an identity matrix while doing row operations on the right-hand side as we go. So Let us try to simplify this. What we're going to do is we're going to keep row 1 the same. And then the second row we're going to do, we want to get to RREF, so we're going to take 4 times the first, 4 R1s minus 3 R2s. That'll give us a 12 minus 12, or a 0. So copying the first column, sorry, first row, copying the first row. Second row is going to be 4 times this, 4 times this is 20, minus 3 times that's 21, 20 minus 21 is negative 1. 4 times this minus 0, 0 minus 3 times this, so minus 3. So this is the same thing we did when solving equations using row operations, only now we just have a bunch of ancillary columns to worry about instead of just the one column. So you have done this before, I guarantee it. All right, let's keep going. Again, we're looking for an identity matrix on the right-hand side here. There's 2 things we can do for that, I think, to help us achieve that goal. The first is to take R1 plus 5 times R2. What that'll do is get rid of this 5. It'll be 5 minus 5 will be 0. And just because we almost have a 1 here, let's do negative R2 for the second one. So let's do the first part first. So 3 minus 0. So sorry, 3 plus 5 times 0 is 3. 3 plus 5 times minus 1 is minus 5. That's going to be 0. R1 plus 5 times this. 1 plus 5 times 4 is 21. This plus 5 times this is negative 15. So again, first row plus 5 times the second row, this plus 5, this plus 5 times this plus 5, and so on. Then the second row we're going to keep the same except flip all the signs. So 0, 1 becomes negative 4 and becomes positive 3, just flipping all the signs. Why is that nice? Well, because now we have a 1 here, and oh my god, we're actually there. Let's just do one more step. Let's do 1/3 of that first row and just copy the second row. So we're going to have dividing by 3 in this whole row turns out nicely. It's like we prepare these examples or something. All right, there we go. Then 0, 1, minus 4, 3. Aha! This is now our 2 by 2 identity matrix. And this, I would claim, is our A inverse. So A inverse is equal to a matrix built out of 7, negative 5, negative 4, and 3. Done. Now, you might have a thought, wait, look at what we started with. 3, 5, 4, 7, 3. Is it that easy? Is it like a little pattern that works for this? Yes, there is a nice pattern for 2-dimensional matrices and their inverses. We'll see a nice generic formula for that later. It's important to have the general procedure at your fingertips, though, or in your toolkit. What we're also going to see is, sadly, as soon as you get past 2 by 2 matrices, like so many things, life is not quite as kind. So we're going to see that next with a 3 by 3 example.